So let us start off with the thing, phase of the wave. In a very easy one, we don't have uh, shouldn't be too much concerned with it. Quite an easy concept, but this is the thing that we introduced just a little in O-level physics also. And matter of fact, we discussed the points, the particles on the wave, whether they are in phase or out of phase, and that's it. So either we are able to answer if the points are in phase or out of phase, but we are not able to calculate the exact phase of the point, or the phase difference between the points, or the phase difference between the between two waves according to O-level physics syllabus. So let us start off with this one first by defining the phase itself. So let us define the phase first before we do anything. So phase, first of all, it is a physical quantity which is represented by the letter, which is represented by the symbol phi. So we'll be using this symbol to represent phase. And phase is position of a point on wave relative to a reference point. So this is how we define phase of a wave. Position of a point on wave relative to a reference point. Now position can be in different, it could be in many contexts. Like, do we define position in terms of the direction? Do we say it's on the left side or on the right side, upwards, downwards? The position can also be in terms of the distance, like from the reference point is 2 meters away, 3 meters away, 4 meters away. It could also be in terms of the distance. And likewise, position can also be in terms of the angle. And for the phase, we define the position in terms of the angle. Like, what is the angle of a point on the wave? That would be defined by that would define the phase of that point. So it is represented in radians or degrees. Those two are the units for the angle. So the phase would be represented in degrees or in radians. So let's check out this case where we have translated the motion of a circle, the motion of an object in a circle, onto a wave. So let's say an object which is being moved in a circle follows the circular path, and if we trace the circular path into the form of wave, it would look something like this. So what do we say? As the object completes one full circle, one full wave is completed. So a full circle corresponds to a full wave. Likewise, if the particle travels half of the circle, that corresponds to half of the wave. Half of the circle corresponds to half of the wave. Likewise, if the object travels or covers quarter of a circle, that corresponds to quarter of the wave. So you see here we have mentioned the corresponding points. Half of the circle corresponds to the point 4 over here, and upon the wave it goes over here. Now why do we do that? So we can see how much angle, or what would be the angle of a certain point on the wave. So if we just take a look at the circle, it would be very easy for us to define the angle for that point, or to state the angle for that point. For example, at the start of the circle, you have 0 degrees. At the start of the circle, you have not covered any angle, so the angle is 0 degrees. So let's say as I move to the point 4, so we can say the angle at this point is 180 degrees. So the phase for the particle which is at position 4 would be 180. At that specific position, it would be 180. And likewise, if I have a particle, let's say at the position 2, the phase for that one would be 90 degrees, because it would be in the middle of 0 and 180. It would be 90 degrees. And likewise, if I have a particle that is at position 6, so you add 180 plus 90, it would be 270 degrees. And as you go back to the same point after completing the circle, or after completing the wave, you get 360 once again, or you can also write it as 0 degree. All the multiples of the integral multiples of 360 can also be written as 0 degrees. For example, 720 degrees can also be written as 0 degrees, because you complete two full circles, two full cycles, and you return to the same point. So the phase would be 0 degrees. So what is the phase? Position of a point on a wave relative to a reference point, and the reference point is the starting point, which is 0 unless mentioned otherwise. And if they mention otherwise, then the concept of phase difference is introduced. And if they ask you for the phase difference, then they'll mention the 2 points explicitly for which they're asking you for the phase difference. So this quantity represented by phi. This is how we define it. It is measured in degrees or radians. And let's talk about the radians also. So in a full circle, we have 2 pi radians. Half of the circle, in half of the wave, we have pi radians. So the phase at the point 4 for the particle 4 would be pi radians. Over here, it would be pi by 2 radians. And if we have something in the middle, it would be pi by 4 radians, which in degrees would be 45. And how do you convert these to? Ratio method. The simplest of them all, the method of the ratios. So what do you do in that? You say 360 degrees equals to 2 pi radians. And let's say if you have 170 degrees, that would be x radians. And then you can find the value of radians from there. So calculating the phase angle, what do? We use the ratio method. We use the method of ratios. So let's say this is the graph for displacement on y-axis and time on x-axis. So we call this displacement time graph. This is a displacement time graph. And if I measure the time from here all the way up till here, in which one wave cycle is completed, what do we call that time? We call it time period, which is represented by capital T. It is represented by capital T. So for a full wave for which the time period is capital T, what is the total angle that is being covered? What is the total phase? It is 360 degrees. For the full circle, for the full cycle, for the full wave, we have 360 degrees. So we say for 360 degrees, there are 360 degrees for time of one cycle. For the full wave, we have 360 degrees. And for a point, which is, let's say, at a value of small t, the phase angle would be x. Now this point t could be anywhere, depending on the point for which they are asking you for the phase. Let's say the value of small t could be 0.1 second, 0.2 seconds, 0.3 second, 0.5 millisecond. It could be anything. And the point small t could be anywhere. Could be here, could be here, could be here, could be anywhere. But wherever this point small t is, you just write down the value of it. And for that time, for the particle which is there at that time, the phase would be x. And then you cross multiply. You say x into t equals to t times 360, and x equals to t divided by capital T times 360 degrees. And what is x representing? X is representing the phase of the particle at that time. So x equals to phase, and now we have a standard formula for phase, which is essentially just a byproduct of cross multiplication. So either you can cross multiply by yourself, just do it manually, or you can directly write down this formula in order to find phase of a point on the wave. And what kind of questions are asked and how do we apply this equation? I'll show in the sample questions, but this is the formula that we have. And for the same one, if we have to find in radians, we can say instead of multiplying by 360 degrees, we'll write 2 pi radians here. So this is the second expression that we can write. Likewise, let's suppose displacement time graph is not given. Rather, they have provided you with displacement distance graph. So instead of displacement time graph, they have provided you with displacement distance graph. So we have distance on the x-axis. So for the full wave, we have 360 degrees, but you know this thing now, that the separation from here till here, it doesn't represent time period now, it represents the wavelength. So this separation is your wavelength. It is the length of one wave. What do we say? We say for one wavelength, we have 360 degrees. And for the given distance, we can cross multiply. So for one wavelength, we have 360 degrees. And for the given distance, the phase would be x. And you get the same expression. You see, if I write it down like this, x times lambda equals to d times 360. Then lambda would be shifted on the other side. It would be d divided by lambda times 360. So that is the other expression for phase if you're given with displacement distance graph. So phase in that case equals to given distance divided by wavelength of the wave times 360 degrees, and for the radians you have the same thing, distance divided by wavelength times 2 pi radian. Or you can also do cross multiplication on the spot and you'll be getting the same answer by that method as well. And matter of fact, this is also cross multiplication. As you can see, it is just a byproduct of cross multiplication. So now we have memorized these expressions in order to find phase of any point at any instant of time or at any given distance from the source. Now the next variation is the phase difference between 2 points. So very easy concept. If you understand the phase itself, finding phase difference would be very easy. All right, phase difference between 2 points. This is the next topic that we have, or I should say the next variation. So in order to find phase difference between 2 points, you could be asked to find phase difference between 2 points between 2 points that lie on the single wave. 2 points that are present on the same wave, that lie on the same wave. So the question can be asked in two different ways. One of the situation is that you're provided with displacement distance graph, and the other situation you would be provided, you can just change this one, you would be provided with displacement time graph. So x t graph and x d graphs. So what do we do for this one? So let's say they ask you to find the phase difference between the point. Let's say here we have the first point A. They ask you to find the phase difference between the point A and the point B. Phase difference between the point A and the point B. This is what we need to find. So what we're going to do is, first I'm going to use the same method. I'm going to find the phase of the point A, then I'm going to find the phase of the point B, then I can find their difference. So let me first find the phase of the point A. Phase of point A. So I'll just take a look at the graph and then I'll recall which formula should be used, and I can see, because we are provided with distance, so I can use this one. Distance divided by given distance divided by wavelength of the wave times 300 degree over here. So I'm going to find the phase of the point A. So the distance of the point A, it is at a distance of, as you can see clearly, it's exactly in the middle of 0 and 2. It's at a distance of 1 meter from the source of the wave. So 1, that's the value for distance for the particle A, divided by, what's the wavelength of the wave? Wavelength of the wave is the length of one complete cycle. If I highlight that one slice at the top, one slice at the bottom, that makes one complete wave. So we have 4 meters as the wavelength. So divided by 4 times 360 degrees. And if you hit it on the calculator, you get 90 degrees. So the phase of the particle A is 90 degrees. And if you be slightly more perceptive, you could have just told it straight away that the phase of the particle A is 90 degrees 90 degrees. I don't know why do I keep saying Celsius or Fahrenheit with it. So the phase of the particle A would be 90 degrees because it's exactly in the middle of 0 and 180. So let's find the phase of the particle B. I'll be writing the same formula, d divided by lambda times 360 degree. I'll stop at degrees. And what is the distance of the particle B? It is at a distance of 2 meters. Divided by what's the wavelength? Wavelength is same because we have a same wave. So divided by 4 times 360 degrees. If you hit it on the calculator, you get 180 degrees. So the phase of wave A is 90. The phase of the wave B is 180. What's the phase difference? The bigger value minus the smaller value. Phase B minus phase A. Just do bigger value minus smaller value. 180 minus 90, you get phase difference of 90 degrees. Now this is how you can find the phase difference between 2 points. But what if I give you another way by which you can find the phase difference between 2 points, and a very simpler way, and matter of fact a shorter way that you can find directly phase difference between point A and B. Well, if we just change the expression and we, instead of writing the distance, we write delta D, which is the separation between the 2 points, and everything else would be written as it is. So what is delta D? Delta D is the distance between 2 points on distance time graph. If you're provided with distance time graph, and if you're provided with displacement time graph, if you're provided with displacement distance graph, then delta D is the distance between the 2 points. If you're provided with displacement time graph, then delta T would be used. The expression would be delta T divided by capital T times 360. Delta T would be the time difference between 2 points. So delta D in that case is the distance between the point A and point B, the separation between the point A and B. This is your delta D. How much is that? A starts from 1, B ends at 2. So the separation is 1 divided by what's the wavelength? 4 times 360. You hit it on the calculator, you get 90 degrees. And that's the phase difference between the points A and B. And let's say in the next case, you're provided with displacement time graph. And I have a point over here. Let's say one point over here, exactly at the start. Okay, not at the start. Let's say one point over here, point A over here, point B over here. And we need to find the phase difference between the point A and B. So what do we do first? We write down the formula, the shorter one, delta T divided by capital T, because we have displacement time graph, times 360 degrees. What is delta T? The separation, the time separation between these two. So A is at 1, B is at 3. What's the difference? 2. What's the time period? Time period is time of one wave. One wave ends in 4 seconds. So divided by 4 times 360 degrees, and it would be 180 degrees. And once again, if you be slightly more perceptive, you can straight away tell this thing that A at the top, B at the bottom. So A would be, as a wave moves to the right side, just as particle A starts to go down, particle B would start to go up. And when particle A is at maximum position, the particle B is also at the maximum position, but on the other side. And hence, they are like the vertically flipped images of each other. That's why we say the phase difference is 180 degrees. So what does that look like? So this is what a phase difference of 180 degrees between two particles would look like. So you see, as one of the particle goes to the max, the other one goes all the way on the other side to the max. And the phase difference between these two is 90 degrees. If I change the particle and I bring one of the particle over here. Now particle A, you can say the phase of the particle A itself is 0. And the phase of the particle B is 90 degrees. Now what is the phase difference between these two? 90 degrees. Or in simple words, you can say the separation between the 2 points in terms of the angle is 90 degrees. And if I bring the second one of them, let's say exactly on the same, so the phase difference in that case would be 0 or 360 degrees. Now these 2 points are in phase. The phase difference is 0. The 2 points are in phase because these two particles are like twins. They're doing everything together, going downwards together, being at the same place, being at the same displacement, going to zero at the same time. So we say these two particles have no phase difference, or these two particles have a phase difference of zero, or these two particles are in phase. And if they are like opposite to each other, we say they are out of phase. The two particles, if they have a phase difference of 180 degrees, then these two particles are called as particles out of phase. Okay, the next variation is the phase difference not between two particles. Now we have to find the phase difference between two waves themselves. And generally, whenever they ask you this question, in order to find phase difference between two waves, they ask you to find phase difference for two waves which are coherent. And at this stage, I can simply tell you coherent waves are the waves which have constant phase difference. Waves with constant phase difference. So whatever their phase difference is, that phase difference would remain same everywhere. It won't change, it won't increase, it won't decrease. If the phase difference remains same, then the two waves are called coherent waves. And also, if two waves have same frequency, then automatically their phase difference would be constant throughout. If they have same time period, which is once again just saying that they have same frequency. If they have same frequency, if they have same time period, then they would always be coherent because they would be having same phase difference throughout. Once again, they can ask you to find phase difference between two waves through displacement distance graph and through displacement time graph. Just change the next one to displacement time. So for the first one, I'm going to draw a situation. I'm going to draw the second wave on this one, and the second wave is given something like this. And then they ask you the question, find the phase difference between two waves, between the black wave and the blue wave, from displacement distance graph first. So what do? How do you find phase difference between two waves? Now the first question that could be there in your mind, that if we have to find phase difference between two waves, which 2 points should be used in order to find phase difference? Because for the first one, for the phase difference, we have same formula. Because we have displacement distance graph, so I'm going to use this one. Divided by lambda times 360 degrees. We use the same formula. Then the question is, how do we find the value of delta D? And matter of fact, they haven't specified any 2 points. Because the thing is, this time, you have to find the phase difference between the two waves themselves. So what you can do is you can take any 2 points, any two consecutive in-phase points of the two waves. Any two consecutive in-phase points of the two waves. For example, if I choose this point for the first wave, which is the point at the maximum amplitude for the black wave, then what is the point for the maximum amplitude but for the blue wave, which is adjacent to this one? It is this one. So either you can choose these two set of points and you can find the distance between them, that would be delta D. For example, this one is at distance of 1, the second one is at 3. So what's the separation? 2 divided by wavelength. Once again, the question is, which wavelength do we use? Do we take the wavelength of the blue one, or shall we take the wavelength of the green one? And the thing is, both of the given waves would be having same wavelength. They would be having the same wavelength. Only then the phase difference can be constant, and they are always asked you to find phase difference if it is constant, which is for coherent waves. So what is the wavelength? If you try to find out the wavelength of the black one, it would be 4 meters. Let's say this one is meters. If you find the wavelength of the blue one, that is also 4 meters, because the blue wave also completes in 1 second. In 4 meters. So let's say the blue one starts from here, goes all the way till here, from 2 to 6, the wavelength is 4. Or if you consider the black one starts from here, goes all the way till here. Yeah, how much distance is covered in one cycle? 4 meters. So the wavelength is 4. So divided by 4 times 360. So if you hit it on the calculator, you get the phase difference of 180 degrees. And once again, if you be slightly more skeptic and more perceptive also, then you can also say that these two waves would be having a phase difference of 180 degrees because they are flipped images, vertically flipped images of each other. Likewise, let's say we are given with the second case, displacement time graph, and the second wave is given something like this. So let me first draw the second wave before I could do anything else. Gotta be careful with it, especially with the points. So the second wave is given something like this. Okay, something like this. Should be slightly more smoother, but let's just go with this one anyway. So this is the second wave that we have provided, the green one, and we need to find the phase difference between these two waves. What do we do? What's the first step? First step is to write down the formula. This formula should be in terms of time. So this should be delta t divided by capital T times 360 degrees. And both the waves should be having the same time period. Only then they'll ask you to find the phase difference. They ask you to find the phase difference for coherent waves. What's the next step? We have to choose two consecutive in phase points, or two consecutive corresponding points on the two waves. For example, if you choose the point 0 for the first one, so this time I'm not going to choose the points from the peak, from the crust. Rather, I'll try to choose points from, let's go with, yeah, we can go with this one, for example. So this point of the black wave is in phase with this point of the green wave. Why? Because at this point, if you consider this point, after this point, what do you see? The crust starts for the black wave, and for this point, for the green wave, the trough starts for both of them after the chosen points. So either you can choose these 2 points for which the difference in time would be, this one would be 1, the second one would be 2. So the difference would be 1, delta t would be 1, and the time period would be once again 4 times 360. The answer would be 90 degrees. Let's choose some other points. I want to choose peak of the first one over here and the peak of the second wave. So these 2 points are also in phase. These 2 points are consecutive in phase points or adjacent in phase points for the 2 waves. In phase and adjacent, like one after the other. Exactly one after, consecutive points. In phase, consecutive in phase points on 2 waves. So the first one, the green one, it's at a distance of 0. The other one is at a distance of, not at a distance, at a time of 0, and the second one is at a time of 1 second. What's the time difference? 0 and 1. The time difference is 1 divided by 4 times 360, because capital T is time period, which is still 4 seconds. So you get 90 degrees once again. So let's take a look at this question we had over here. If we consider these 2 waves, and just let me remove everything, at least for now. We are provided with 2 waves, wave P and wave Q. I can mark it for you. I can highlight this is a wave P. So the highlighted one is a wave P, and the other one would be definitely wave Q. Now we can see them distinctly. So what do we need to find? We need to find the phase difference between 2 points. Not 2 points. My bad. Phase difference between 2 waves. We need to find phase difference between 2 waves. What do? We scroll all the way up to the graph, and we see what graph do we have. Do we have displacement distance? Do we have displacement time? For example, in this one, we have displacement time. So we write down the formula accordingly. That phase difference between the 2 waves would be delta t divided by t, capital T, which is the time period, should be same for both of them, times 360 degrees. So what is delta t for this one? You need to first pick up 2 points, and these 2 points should be corresponding. If I be very precise, the 2 points should be consecutive in phase points for the 2 waves. So for example, pick the point crust at the crust of the first wave, then crust of the second wave. You can go with that. Find delta t between these 2. Or if I keep it easier, I can pick this point from the first wave, and the point that is in phase with respect to this one is over here. So check it out, these 2 points. How do we know? Because the wave P, after this point, the wave P goes all the way up. Likewise, after this point, the wave Q also goes all the way up. Just explain layman terms. You don't answer like that the wave goes all the way up. But once you have found, or once you have marked the points, what do you do afterwards? You find delta t. So the difference in time between these 2 points would be 0.20. So I'll be writing 0.20 here, because that's the difference in the time between these two divided by capital T. Capital T is time period of any of these two waves, because it would be same for both of them. So I'll just try to find out the time period of this one. Completes over here, 0.60 seconds times 360 degrees, and I can remove the extra stuff. We open up the calculator, we do 0.2 divided by 0.6 times 360 degrees, and we get 120 degrees as the phase difference between two waves. And 120 degrees is once again very frequently asked phase difference, 120 degrees. So what do we have? We have, first of all, phase of a point. This question can be asked in 3 different ways. We have phase of a point, then we have phase difference between 2 points on the same wave, then we have phase difference between 2 waves themselves. And everything comes with 2 graphs. Either it could be asked from displacement distance, or they can ask you from displacement time graph. And coherent waves, you can write over here, waves that have constant phase difference throughout. Phase difference throughout. And if they have same frequency, if they have same time period, and if you're provided with displacement distance graph, if they have same wavelength, 2 waves, then that would imply that the 2 waves are coherent and they're going to have same phase difference throughout. If the phase difference is, let's say, 60 degrees, it will remain 60 degrees all the time.